So in the last lecture, I talked about the concentrations of greenhouse gases in the atmosphere, and now what we're going to do is look at longer-term records of greenhouse gases in the atmosphere from a range of different proxy indicators, particularly from bubbles of air trapped in ice. But before we get on to that, we need to understand how we can use the information from what are called different isotopes of carbon. Atoms which have different numbers of neutrons in their nucleus, and the same way with different isotopes of oxygen and how they can be used for inferring information about variations of carbon dioxide or variations of water in long-term climate variations over hundreds of thousands of years. So what we're going to do is start first of all by looking at these isotopic variations. We're going to look at isotopic variations of carbon, and there are in fact three different isotopic forms of carbon. Carbon-12, which is the most common version, has 6 electrons orbiting around the nucleus and 6 protons and 6 neutrons, giving it an atomic weight of 12. But then there's a carbon-13 version, which has 1 extra neutron, and that gives it an atomic weight of 13. And then there's finally a very, very rare but carbon-14 version, which has 8 neutrons, and that is radioactive, and it has a half-life or a decay time of 57,000 years. Sorry, 5,730 years. Let me get it right. The other two versions, carbon-12 and carbon-13, do not decay, they're stable, but carbon-14 is radioactive and decays slowly with a 5,700 year half-life. So why are those very important, and how is carbon-14 made? Well, carbon-14 is made by cosmic rays. Cosmic rays come from the sun and from the intergalactic material. They will intercept with nitrogen, and that nitrogen, when the cosmic ray comes in, it will be absorbed by the nucleus of a nitrogen atom that will then produce carbon-14, and a proton will be shed. That carbon-14 will then be taken up in water, taken up in plants, taken up in ice, and eventually it'll be released into the atmosphere. But it decays, and as the carbon-14 decays, the amount of carbon-14 will be reduced relative to what's normally in the atmosphere. And because carbon-14 decays over time, it means that the actual amount of carbon-14 in something which is, if you like, has no longer interacting with the atmosphere at the time. For instance, plants that have died will no longer take up carbon-14. They'll lose their carbon-14 because it will decay, and we can use carbon-14 for looking at the age or dating of dead organic matter. And this carbon-14 dating is used in lots of things, dating old pieces of wood, but it can also be used for dating carbon dioxide when it's trapped in air bubbles in ice. There's only about 7.5 kilograms of carbon-14 produced annually by cosmic rays. And that's a very, very, very small fraction of the annual human production of carbon dioxide. But this can still allow us to assess how old or how new carbon dioxide that's being produced by looking at the ratio. One of the things that we can see by comparing the amount of carbon-14 in carbon dioxide that's being produced now in the atmosphere versus the standard atmospheric concentration is that the carbon-14 amount in the atmosphere, in the new carbon, the carbon-14 amount is falling. And that means that the carbon dioxide being produced by human activity is old carbon, old carbon because it's coming from primarily fossil fuels. And so the carbon-14 amount in the atmosphere is falling. Not by much, but falling, exactly to match the expected change due to burning of fossil fuels. So now let's look at carbon-13. And the really interesting thing is that photosynthesis enhances carbon-12 relative to carbon-13 in plants, and it enhances carbon-12 relative to carbon-14 in plants. In fact, it's the lighter versions of the atom of carbon, carbon-12 relative to carbon-13 and carbon-12 relative to carbon-14, that are taken up in plants by photosynthesis. So that means that there's an enhancement of carbon-12 relative to carbon-13 when we look at fossil fuels. And therefore the fossil fuels contain less carbon-13. When we then burn the carbon from fossil fuels, when we burn the fossil fuels, the carbon dioxide produced has less than expected amounts of carbon-13. As we add more fossil fuel carbon dioxide to the atmosphere, the amount of carbon-13 will fall. And what we're going to do is look at the changes in concentration. I talked about that a little bit in the last lecture, and what we're going to do is to see how much the carbon dioxide ratio of carbon dioxide with carbon-13 versus the carbon dioxide with carbon-12 has changed over the last 40 years or so. And that's exactly what this graph shows. The top part here shows the increase in carbon dioxide concentrations over the last 40 years or so. And down here, we see the changes in the carbon-13 amount. And we can see here that the ratio of carbon-13 in this graph has fallen exactly as you would expect, associated with the increase in carbon dioxide if it was due to burning photosynthetically processed material. And yes, fossil fuels are photosynthetically processed material. We can also see that this is entirely consistent with the changes both from oxidizing something, and up here is shown the oxygen concentration. I showed this in the last lecture as well. So we have two pieces of evidence. Changes in carbon dioxide from burning fossil fuels would be expected to lead to reductions in the oxygen concentrations as well as reductions in the isotopic amount of carbon-13. There are a few scientists who say that maybe the increase in carbon dioxide is due to volcanoes. And this is clear evidence, because if carbon dioxide was coming from volcanoes, it wouldn't deplete the carbon-13, nor would it deplete the oxygen amounts. So it is absolutely certain that the increases in carbon dioxide in the atmosphere over the last 50 years are definitely not due to increases in volcanic eruptions. And no, a single volcano has not caused an increase in carbon dioxide, nor has a series of volcanoes over the last 50 years. It is true, hundreds of millions of years ago, that volcanoes did cause the increase in carbon dioxide in the atmosphere. Geological processes were important. They just aren't causing this modern increase in carbon dioxide. What about other variations? Well, it's really interesting that we can use the changes in the isotopic amounts of oxygen in water. And oxygen occurs in two separate forms. Again, stable forms, oxygen 16 and oxygen 18. And as water evaporates and then condenses, it's the oxygen 16 which is enhanced relative to the oxygen 18 as the water evaporates from water bodies. So oxygen 16, the version over here, is enhanced in evaporation. So we can use that variations of the oxygen 16 to oxygen 18 ratio either in ice caps, when we look at the amount of ice, to determine how old the ice is and what was the temperature of that ice. So, as I said, there are three different versions. Oxygen 16 and oxygen 18 are the ones that we look at. They're much more common. There is an oxygen 17 version, but that is extremely rare, and they have fairly similar, well, almost identical chemical properties. So these are stable isotopes, oxygen-16 and oxygen-18. They have the same chemical reactions, but actually when they evaporate, the lighter oxygen-16 evaporates first. The oxygen isotopes are very important, and much like with the carbon isotopes, the lighter element of water evaporates more quickly, so the water with oxygen-16 evaporates more quickly, and water with the oxygen-18 isotopes falls out of the rain or condenses as rain falls. So that means that rain is enhanced in oxygen-16 compared to oxygen-18 because the oxygen-16 has evaporated, and then as the rain or the clouds move from the tropics to higher latitudes, the oxygen-18 in the water will have preferentially fallen out because it condenses more quickly. So when we look at air traveling from low latitudes into polar regions, as it goes higher and higher latitudes into colder and colder air, there's more and more water has fallen out, more rain has condensed, and as it's condensing, the air as it gets to higher latitudes has enhanced oxygen-16 compared with oxygen-18. So at high latitudes in the colder climates, we're going to have enhanced water, and in this case frozen water or ice with oxygen-16 in it. So if we look at this curve, we see depletion of oxygen-18 water here at the very cold temperatures and more oxygen-18 in the water at higher temperatures. So now we can then look at how this has varied over time. Here this scale goes from older times to more recent times. This is more recent times with more oxygen-18, and colder times there was less oxygen-18 or more relative oxygen-16 amounts. And this temperature scale corresponds to the change between an ice age and an interglacial period. It's about 7 degrees warmer in the interglacial period in Antarctica, and this is where this ice core has come from. It's the same in Greenland, where change between a glacial period or an ice age and an interglacial period is of the order of 7 to 10 degrees, and that can be inferred from the changes in the amount of oxygen-16 and oxygen-18 in the water. So if we look then at scales for temperature variations globally, the global temperature variations from the last ice age, which finished about 15,000 years ago, and present day temperatures are around 5 degrees temperature variations. And then for the period of the climate over the last 10,000 years, we've actually had a relatively stable climate. And here in the future, we don't know what's going to happen. We're going to look at that in later lectures. So what we've talked about recently is the temperature variations and how we can infer those from ice cores. So let's look now at some of this evidence. We can get ice cores from a range of different locations by drilling deep ice in Greenland, where the deepest ice is more than 1 kilometre deep, and that allows us to get information from over 100,000 years ago, and also from Antarctica, and in the East Antarctic region we can drill ice which is 4 kilometres long, and that allows us to get ice variations that are at least 400,000 years old, and in fact the most recent data provides information that is about 800,000 years old. And we can use that data both to look at the changes in the oxygen-18 to oxygen-16 ratio to infer temperatures, and from the air bubbles that are trapped in these ice cores, we can extract out the air samples and get information about the changes in carbon dioxide variations. And this graph shows the temperature variations up here and the carbon dioxide variations down here. And the highest carbon dioxide at any stage over the last 400,000 years between these regular cold periods and the interglacial periods is the highest concentration is around 280 parts per million. But notice where these vertical bars are that there's nearly synchronous variations in carbon dioxide and temperature. In fact, in the Ice Age and interglacial cycles, which happen about every 100,000 years, and those we've said already are associated with changes in the Earth's orbit around the Sun, there's also large carbon dioxide variations. But in this case, the carbon dioxide variations are initiated by the temperature changes. And we're going to look at the causes of how the carbon dioxide is affected by the water temperature when we look at feedback processes a little bit later in this course. But when we look at carbon dioxide variations and temperature, we see quite a strong relationship. In this case, though, the temperature variations are driving the carbon dioxide, and it may not be appropriate. But let's look at these Ice Age and interglacial variations associated with the carbon dioxide variations and try to make some inferences about the changes in temperature and changes in carbon dioxide. Remember, modern day carbon dioxide is way out here at 400 parts per million. So what would be the appropriate scale if we look using this relationship from the Ice Age and interglacial cycles for the temperature variations? We would say that actually this, if the same relationship held, would be the appropriate warming. And that would mean that the temperature increases would be 7 degrees warmer than at present. Now, there are a number of problems with this argument, and in particular, it is that the change from the last glacial periods to the current interglacial was associated with major changes in ice cover. And we don't have that much ice anymore, so we can't expect the same change in climate. But we will look at some of these feedback processes and the inference for future climate in a later class. So what I've talked about is how we can use carbon isotopes and water isotopes to look at understanding the causes of modern climate variations, particularly the causes of carbon dioxide variations, and also looking at long-term variations from ice cores or other climate records. And we can infer using ice cores changes in climate and changes in carbon dioxide over the last 500,000 years to 1 million years.